Okay, so please now move to the... Okay, so this is what I will talk about. It's about neutron stars, binary neutron stars. I'll tell you why it is interesting to study binary neutron stars. And I'll try to give you a very quick, but hopefully comprehensive introduction to the anatomy of the gravitational wave signal from binary neutron stars. I hope you will appreciate what are the main features. I will tell you something about magnetic fields and electromagnetic counterparts, the ejected mass and nuclear synthesis, and now how this single event has already given us a lot of information about what are the typical, what might be the maximum mass and radii of neutron stars. Again, please interrupt me anytime you have a question or I'm not clear. So this is we're theorists here, and so at the end of the day we want to look at our problem in the simplest possible way and broken up in its elementary part. And so all of this is just a binary problem, okay? You take two objects, they are just interacting gravitationally, you give some linear momentum, you study the equations of motion, that's all, right? Of course this will entail calculating gravitational waves. So if you have two black holes, it's a binary problem, and you can think this is a scattering problem. You start with two black holes and the end result is another black hole plus gravitational wave. That's a very simple description of the problem. And this is not just fantasy, this is actually something we measured. Piotr has already discussed this in great depth. This is the first time we've seen this happen in nature. And Omega Relativity was predicting this signal 10 years earlier. Now, there is another binary problem that you can think of, and this is a binary neutron star problem. So now you have two objects which are neutron stars, okay? And so again, if you break up this process in the simplest possible elements, you have two neutron stars, eventually you end up with a black hole plus gravitational wave. So pretty much it seems like the first state and the end state is very similar. But there are important subtleties, and there are two subtleties. The first one is that when you have this process happening, it doesn't happen that immediately produce a black hole, unless you are in very special situations. Most of the time, what you produce is called a hypermassive neutron star. This is a star which has a very large mass, which is kept alive because it has a lot of differential rotation, but is also made unstable. So we want to collapse to produce a black hole, and so. When it does so, when it produces a black hole, some of the matter will be in unstable orbits. And so you will produce a black hole, but also a torus. And eventually, when the torus is accreted because of dissipative effects, you end up with a black hole in vacuum.
But what about electromagnetic radiation of, for example, neutrino radiation?
Right. So this is where all the question marks are. Okay. So if we understand this part over here, maybe we understand what are the properties of the equation of state. And neutrinos will play a role in this part over here. If we understand this part, then maybe we have a way of understanding what produces short gamma ray bursts. Nowadays, we have a clear indication that the two things are connected. Binary neutron stars and short gamma ray bursts are connected. But how you produce a short gamma ray burst in practice, this is still, unclear. And there is another important part of this process, which is the ejected matter. Now, you have to think that essentially you are taking two objects which are of the size of the sun in terms of mass. You are colliding them at a fraction of the speed of light. You can imagine that some of this matter will be lost, right? It's unbound, and some of this matter will have very large number of neutrons. Will be neutron rich. This will decay and produce nuclear synthesis. So a lot of the heavy elements, as I mentioned, are produced by this process. So we think that essentially all of the gold in the universe is produced by this process, because any other alternative is not as efficient. So it's clear nowadays that binary neutron stars do produce gold. It's not clear they produce coins, but they certainly produce gold. So in general, and I would have shown an animation at this point, which I can't, there is this sequence of events. You have a merger, you have an upper mass neutron star and a black hole plus torus. This is very robust. You can do and be as sophisticated as you wish. This is always be there. And so if you want to look at what are the quantitative differences in this picture, the first one is the total mass. And this is responsible for what is called a prompt versus delayed collapse. to appreciate this, I'll show you this in this cartoon, which is a funny cartoon because I have time on the x-axis, and it's a funny axis because it's, you know, it's really snapshots of different times, and I have on the vertical axis, I have the mass of the system normalized to the maximum mass that a neutron star can support, which is called m max. We don't know what this is, that's why I normalize it. But you can think that if the system is roughly in this range, well, you know, then this is what is going to happen. The binary is going to inspiral for 10 millions of years or so. It will produce this hypermassive neutron star, which is a highly distorted object, will produce a black hole, a torus, and then eventually will produce a black hole in vacuum. And all of this takes about 100 seconds from merger over to the final black hole. Now, this is the vanilla configuration. If you assume that the neutron star will have something like 1.4 solar masses and the maximum mass is of order 2.2 solar masses, this is what you would expect. And guess what? It is exactly the ballpark we've seen in the observation. You can crank up the mass of the system and have a larger mass, in which case, well, you know, this guy simply doesn't exist. There is so much mass that the system cannot support it. There is no equation of state that will be able to produce enough pressure, no rotation that will counter gravity, so you immediately produce a black hole. And conversely, you can lower the mass of the system and have something which is smaller, say something over the order of 1 solar mass per star. Well, this is something quite interesting, because if this happens, you don't produce necessarily a black hole. In fact, you know, you might produce something which is a uniformly rotating object, or maybe it's called a protomagnetar. Some observers would like this to happen, because this is going to be lasting for very long times. Or if this guy then just spins down, you will end up with a perfectly spherical star, which is in equilibrium, or maybe a black hole, depending on whether this is above or below the maximum mass. So this is essentially the picture, how the picture changes if you allow for changes in the mass. Of course, the other important change is the mass asymmetry. Okay, if you have that the two stars are do not have the same mass, then what is going to happen is that one of the stars, the least massive, will be broken apart tidally. There's going to be a very strong tidal field before merger, and this will break the star apart. This has a number of consequences. The most important is that you will eject more matter, simply because you take one of the stars, instead of hitting it, you break it apart, and so you will spread its matter around. Then there is, of course, another important ingredient, which is the equation of state. And in this business, people like to be oversimplified, talk about stiff and soft equations of state, depending on whether you can take a star and compress it to very small radii, in which case you have a soft equation of state, or you cannot, in which case you have a stiff equation of state. And I'll show you how this plays a role. Then, of course, magnetic fields are important, and they are the ones responsible for both the equilibrium and the electromagnetic emission. And then, as was mentioned before, radiative losses in terms of neutrinos are important, both because the equilibrium and the nucleosynthesis. The neutrinos and neutrino reactions do change the electron fraction, and this has an impact on how much gold, for instance, is produced. So let me tell you how you can use boundary neutron star waveform to constrain the equation of state. This is, an historical waveform. This was computed by myself in 2006. It's pretty crappy if you look at it by modern standards. It has a number of problems, but it's useful and historical, and I've computed it. So what you can appreciate here that there is a chirp signal. That is a part of the signal where the amplitude grows and the frequency does. So this is called a chirp signal. And then there is a ring down. Okay, so it's a very simple waveform when you look at it. Doesn't have interesting features. This is instead, by comparison, a Bonny neutron star, a prototypical Bonny neutron star waveform. You can still recognize there is a chirp signal. Okay, after all, you have two compact objects in spiraling. Then there is this part over here, which is a transient. Then you have this part over here, which is the one produced by the hypermassive neutron star. This essentially is a bar-shaped object which is rotating and is producing an almost constant frequency, almost constant amplitude signal. And then, of course, you have the ring down. Okay, so black hole formation and ring down. So if you want, you have to compare this guy over here and against this guy over here. In gravitational wave astronomy, it's easier or more interesting to compare waveforms not in time but in frequency. In which case you have to, get your head around and think about frequency evolution. So a binary signal in a frequency space will come from up here and move downwards. It moves downwards because of two reasons. The first one is the system is increasing its frequency, the orbit is becoming tighter and tighter, but the spectral amplitude, so the amount of energy per unit frequency, goes down simply because you spend less time per any energy bin. Okay, so again, typical things is you show the sensitivity of instruments. So this is advanced LIGO. Anything above these curves can be seen, anything below cannot be seen. Now, suppose we make the following experiment. We produce a binary system of black holes with 1.4 solar masses. We don't think they exist, but we can always compute them. And this would be the black line over here. So it would go like this. This is where post-Newtonian provides a very good approximation. Then there is a little bump over here, and then there is a cutoff, an exponential cutoff. The bump is produced by the fact that as you go at very high frequency, there is actually an increase in the amount of energy, so you get more per unit bin. And then there is a ring down, and it is just an exponential cutoff. Now, by contrast, Bonny neutron stars are shown with blue lines. And as you can see, there is quite a difference. Round about here, Bonny neutron stars, remember that they have an extended size. They are 10 kilometers or so. And so they will start interacting at these frequencies. These are called tidal effects. There is a whole industry nowadays in trying to model these tidal effects. Essentially, if you have a star that can be stretched, then this will introduce a difference in the efficiency in which you emit gravitational waves. And as a result, you will merge earlier. Well, simply because the two stars will touch earlier. And so you have that the merger happens around about here, about 1100 Hertz instead of having 5 kilohertz for that mass. And then you see there is a very complicated signal over here, and then there is a ring down as the black hole is produced. So the name of the game is not only to tell the black from the blue, but actually to tell the two blue ones, because there are two different equations of state, and you would like to tell which one is a black, which equation of state is. Another thing you may appreciate is that, this is a very complicated system, and as compared or contrasted with a Bonny black hole, there is a lot of dirtiness in it. Okay, so if you are a purist, then you would think that this is the perfect waveform. There is just no feature, just a little bump. But of course, someone's rubbish, this one is someone else's richness, and I think this is where all physics is. So this is what the kind of things we can do nowadays, colorful plots essentially, where you can see these are different equations of state with different colors, and different columns are different masses. These calculations alone took more than a year on a supercomputing cluster, and I can explain everything you need to know in about a minute. So these are soft equations of state, these are stiff equations of state. You can appreciate that if you have a soft equation of state, the post-merger signal is very weak. Okay, it's a fraction of the pre-merger signal. This is simply because a soft equation of state means that those two stars can be very, very compact, they're very small, and so the gravitational wave signal is small. By contrast, if you have a stiff equation of state, you have a bulky object which is going around, it's producing large gravitational waves, and you see the amplitude here is comparable, maybe 50% as the pre-merger. Also, you can appreciate this is a high frequency signal, this is a low frequency signal. Again, soft means compact, more compact or more high frequency. And of course, you can find that there are intermediate, there is a continuum as you crank up stiffness in this respect. Another thing you can appreciate is that you can't quite appreciate, but this guy here produces a black hole. So this is the largest mass after which you produce a black hole. This is also easy to explain. This is a very efficient emitter of gravitational waves. It's losing a lot of angular momentum. So this guy will very rapidly produce a black hole, while this guy, which is not losing so much angular momentum, will survive for much longer times. So in general, if you want to have the hypermassive neutron star to survive for a long time, you want to have rather low masses and soft equations of state. Now, what you can also do is look at this same information in a frequency domain, and this is what you get. So this is the power spectral density of the same waveforms. And I'm not asking you to appreciate anything here. The only thing I would like you to bear in mind, and I think it's important, is that these are lines. If you have ever studied, yes, sorry.
Sorry, just go back to the
Yep.
previous one. So in the case of the stiff equation of state, we learned decades ago from Chandrasekhar about ellipsoidal figures of equilibrium. Should we think of this as really being almost an ellipsoidal thing, whereas in the soft case it's kind of two discrete objects? Is that a good way to think about it?
Yeah, you know, if that would be a zeroth order approximation, really, yeah. I mean, let's say in this case might be a better approximation.
Leading order, so
Yeah,
it's right.
yeah. I think, you know, this guy might be a reasonable ellipsoid of rotation. In this case, you have that the two stars produce a very widely oscillating object. So the two stellar cores are merging and pounding at each other. And this is why, for instance, you see these beading systems here. Yes. So essentially there you have the system not only is rotating, but is also compressing, and so you have this beading because of the two frequencies being very close. So let me go back to here about these being lines. If you remember, in astronomy, astronomy has become a science when people were able to understand that by looking at the emission and absorption lines of stellar atmospheres, you can tell what was the composition of the stars. And these are not very different. These are lines. They are, you know, spectral features at precise locations in frequencies. And so, if you want, this is gravitational wave spectroscopy. It's a way of learning about a signal by just knowing about the position of lines. And if you don't believe that this is correct, let me show you why this is really possible. So there's been a lot of work, and these are some of the people who have worked in this direction. On top, I'll show you a gravitational waveform for an equation of state, whatever, blue equation of state. This is in time, and this is the spectral representation. So this dotted line is the inspiral. So you can think that this line really should go up here for many orbits. And then you see that there is a big peak, which we call F2. Then there are two more peaks, which we call F1 and F3. You don't need a whole lot of thinking to realize that this peak over here is produced by this part of the signal where the frequency is almost constant. So you have in the Fourier transform a large power. What produces this F2 and F3, which are roughly side bands of F2, is a bit complicated. If I have time, I will explain to you. But for the time being, let's just assume that there are three peaks. Another thing you can appreciate is this circle over here. That's the frequency at merger. That's the frequency of the signal when there is a merger. You just compute it. Essentially, it's a convention, but it's a useful convention. There is no feature appearing here. You just look at the amplitude. When the amplitude has a maximum, you fix the frequency, and that's the merger frequency. Now you change the equation of state. You have a completely different waveform. You can't quite see it, but it's a completely different waveform. And then you ask yourself, okay, do I see something which is robust? So you look at the spectrum, and you find that again you can recognize there is an F2, there is an F1, and F3. And what you can recognize, of course, F2 is a much broader spectrum, as other smaller peaks, but overall there is an F2 frequency, and there is an F1 frequency, and there is an F3 frequency. So what I'm trying to say here is that although the features, the position of the lines is different, the spectral properties are robust, and this is all we need to know. Okay, and so how do you use this information then to extract information about the equation of state? And this is where quasi-universal relations come to help. So what you can, yes, I should remark another thing. So you see here the red circle here has moved to higher frequencies. This is because the red equation of state is a softer equation of state. This means that the two stars are more compact, can get closer to each other, and so the inspiral will will go on for higher frequencies. So the first thing you can do, having done many of these simulations, you collect all of these dots and you plug them against some quantity. So this is what I've done here. I've put F max, that frequency at the merger, versus the love number. Love number has got nothing to do with feelings. It comes from this British physicist who was the first one to compute it, and it's essentially tidal deformability. It's just telling you that if you are a self-gravitating object in another gravitational field, you will deform yourself because of this field. This is a scalar. It's just the first element of a series expansion in multiples. So what this is telling you is that there is a universal relation. So different colors are different equations of state. And in principle, these different colors could be all over the place here. But rather they follow a certain precise relation. And this is very useful because now if you do a measurement of this frequency over here, you have immediately a measurement of the tidal deformability of the system, independently of the equation of state. Okay? And once you have this, what do you do with it? Well, you can use this because this guy over here is related himself to other quantities like the moment of inertia, the quadrupole moment, the compactness. So essentially you have a direct measurement, direct mapping from the observation over to the stellar properties. This was done for the inspiral. You can do this with other quantities, for instance with this, the first frequency after the merger, F1, and you can see there is a very nice tight relation in terms of the compactness. So you can think that if you have measured F1 and if you measure the mass of the system, you have immediately a measure of the radius of the system, well, of the star, of course. And you can do this with other frequencies and so on. So I don't want to go in too much of the details in this, just to show that the spectral properties are robust. We know now how to go from these spectral properties over to the physical properties of the star. And you put this into a data analysis Monte Carlo code, and you end up with the following kind of with the following predictions. If the equations are stiff, then the error in the radius will be less than 10% with 20 detections. Now, I should mention this something. I haven't done this, so I apologize. The part of the signal where all of these peaks are is at very high frequency. And unfortunately, this is very hard to detect. Okay? In fact, with the only detection we've seen, we haven't seen that part of the signal. Unfortunately, it was just going below the... So, although it's very weak, if you have lots of detections, you can stack this signal, and that is why if you have a certain number of detection, your ability to measure things increases. So if the equations of state is stiff, and 20 detection will give you about 10% radius error. Things are much more difficult if you have a soft equation of state, in which case you will need to have 50 detections. Now you see here an example of a theorist's optimism. We haven't seen not even a single one. I'm already telling you what is going to be our ability after 50. You know, it's not going to be too difficult to discriminate between stiff and soft, even with a 10 or so detections. And in principle, if we have a golden binary, so if you have a signal to noise ratio of 6, you know, the expected are of order 1, a 30 megaparsec, which is extremely close, then even a single binary will give us delta R over R at 2%, less than 2% at 90% confidence level. So this closes my discussion about how you can learn about the equation of state from the gravitational waveform. Let me switch over to electromagnetic counterpart. And I'm pretty sure all of you know about gamma ray bursts. There are long and short gamma ray bursts that we think that long ones are produced by very massive stars which collapse in a time scale of about tens of seconds, while the short ones have have been associated historically. I mean, when I say historical, I mean since the 70s, to Bonny neutron stars. And it's just last year that we were able to close the circle and say, okay, Bonny neutron star mergers in gravitational waves are associated with short gamma ray burst. Now, one of the problems is that in the observations you see the evidence of a jet, of a magnetic jet, a collimated jet. And so, but how do you produce a jet out of having two stars which collide? And well, you know, it doesn't take a whole lot of thinking that if you have a jet, you need some magnetic fields, large-scale order magnetic fields. That's what we see in accretion disks. So the question is what happens when two magnetized stars collide? You have to go away from relativistic hydrodynamics. You have to go into magnetohydrodynamics, in addition to Einstein's equations. And these are, you know, the results of some simulations that were carried out in my group, where you show the magnetic field lines inside the star initially. At the merger, you still have pretty coherent magnetic field lines. Then there is the upper massive neutron star stage where everything is sheared and distorted, so that whatever topology you start with, this is going to be pretty much destroyed at this point. And then after a black hole is produced, this is what happens. You know, there is going to be a black hole which is a curved black hole, and so it's going to be rotating. There's going to be a precise direction where things will rotate. There's going to be certain orbits which are allowed and other which are not. And as a result of this, if you wait long enough, you see that magnetic jet structure is produced. This is not yet an outflow. There is not yet matter going out of this. As a matter of fact, the matter is all going in because there is not enough microphysics. But if you look at the the properties of this object, you have a curved black hole of 0.8, 6% of a solar mass in the torus. You have about 3.3 seconds to accrete everything and launch a gamma ray burst. So although this is not a gamma ray burst simulation, this is just a proof of concept that if you take two neutron stars which have magnetic fields and you produce a black hole, then chances are you will produce also a jet.
These are simulations, not artist's rendition.
Yeah. So so this one is artist.
Yeah.
This one is not artist. Yeah. And other artists, you know, other groups have redone the simulations and obtained similar results. So nowadays, there is consensus that if you take two stars and you produce a black hole, it is important you produce a black hole. Because then essentially what happens is very simple. You need a black hole because if you have a black hole and you are a particle and you have a certain angular momentum, on the polar axis of the black hole you will have zero angular momentum. So at that point you have two options. Either you fall onto the black hole or you move out. And that is why in order to produce a jet, you need first to produce a black hole which empties all of this polar region, and then maybe microphysical effects, neutrinos or resistivity will launch a jet. So that is why you do need a black hole to be produced. Let me switch over to the ejected matter nucleosynthesis. As I said, this is another nice aspect of this system. And in the 50s, there are some beautiful papers that have been written by nuclear astrophysicists about how you can synthesize all of the elements inside stars. There are very detailed calculations, and what it was clear that heavy elements, so something which atomic mass number larger than 56, cannot be produced in stellar interiors. So you need to produce heavy elements, and well, at least not efficiently. Okay, you can still dredge some material out from the stellar interior, then lift it up and through a wind release it, but it's not very efficient. On the other hand, if you have a supernova explosion, then you have a way of mixing cards all at once, and you can produce nucleosynthesis very rapidly. And so supernova were thought to be the standard way in which heavy elements were produced. But nowadays, more detailed simulations have shown that it's actually very difficult to produce very heavy elements from supernova simulation. The reason is that you need to start with something which is already very neutron-rich. But a supernova is not yet neutron-rich. In fact, it's just producing a neutron star. And you need very high temperatures, which again are not found in supernova explosion. So what you need is actually neutron star merger. Seems the perfect way. You're already starting with all the right ingredients. The recipe seems perfect. And so when you come down to how you can produce these nucleosynthesis from Bonny neutron stars, I think it's important to distinguish between dynamical and secular ejection. As I said, some of the matter is just lost because of the very high energies, and you can release matter through dynamical ejection, that is essentially shocks, and this lasts around about 100 milliseconds, or through secular processes. This can be magnetic or neutrino-driven winds, and this can last much longer timescales. And of course, these guys we can simulate. These guys we can simulate rather self-consistently. These guys we cannot simulate, but with some approximations. We simply do not have access to such large timescales. What is important is even a small amount of ejected matter. So we're not talking about a large amount of matter. This is about 1% of the total mass of the system is sufficient to observe, to explain the abundances. And in particular, if you look at mass numbers larger than 120, there is a very robust agreement with the observations. And this is independent of the equation of state, the masses of the system, the nuclear reaction taken into account, the merger type, whether you are in circular orbits or in eccentric orbits. And I apologize for the quality of this. But okay, so this is the relative abundance of a given element whose mass number is given here. These are some relevant examples. So this is cesium, europium, this is gold. So there is a second and third peak, which are the typical ones, and the dots are the observed abundances. And you can see that numerical simulations can reproduce this overall trend pretty well, and cannot reproduce a very low mass number. This is where supernova instead are much better. So to give you an idea of robustness, what I meant by robustness, these are different equations of state, different masses, different mass ratios, and as you can see, they all reproduce the data equally well. So if you want to have a mind-blowing thought, this event, GW170817, produced 16,000 times the mass of the Earth in heavy elements. And just in gold, there are 10 planets of Earth, just in gold. Just imagine. Of course, they are not in planets. They are distributed everywhere. So, and another thing, another mind-blowing idea is that, when I was a student in astronomy, I was told, you are son of the stars because of supernova explosion. Now, actually, you have to think again and think we're not just sons of the star, or stellar dust, but actually neutron star dust. Okay, let me come to this guy over here and how this has already had an impact on what we understand. So, I don't think anyone has shown this, but this is the trajectory in frequency and power of this event. GW170817 was seen last August and has been released in October. So this is Hanford, Livingston, and this is Virgo. Virgo doesn't really see much, but is important for the localization. You get all the analyses and you end up with this number over here. You have a total mass of 2.74 solar masses, plus or minus something, and the two component masses are about 1.3, 1.4 solar masses, and the mass ratio is about 0.8, 0.9. So exactly the ballpark that we were expecting from by looking at the system that we know have not merged yet. And in order to appreciate how this simple observation has helped us to set a value for the maximum mass, a maximum value for the maximum mass, I need to be pedantic and guide you through a number of thoughts, a line of thoughts, which will explain it. So let's go back to Blackboard and suppose that you want to study non-rotating equilibria of neutron stars. Then you can solve the equations, which are called the TOV equations, and you end up in a mass central density diagram, a curve like this. Note there are no numbers here because this is true for any equation of state. that there's going to be a rising branch, a maximum, and a decreasing branch. So this guy over here is called the maximum mass of non-rotating configuration. And stars on this side of the branch are going to be in equilibrium and stable. This will be in equilibrium and unstable. In other words, you take this object, you just put in another neutron onto it, and this object will have to collapse to a black hole. You can repeat this exercise by increasing the rotation. These are non-rotating, so you can give some rotation, and then the space of solution will be the one in green. So these are all stable stars which are rotating uniformly. And you can see there is another line, black line, which is the upper limit to this space, and this is given by the solutions at mass shedding. These are all the solutions which are rotating as fast as they can. You take them and rotate them a little bit faster, and you break them apart. So this is called the mass shedding limit. And in this green region, there are all the equilibria which are possible. On this line over here is called the stability line now, and essentially all models on the right of this line are unstable. They are equilibrium, but they are unstable. Vice versa, they are stable on this side. So anything that you put here will collapse to a black hole, and this is called the stability line, as I was saying. Now, there is an interesting universal relation that allows you to tell you what is m max if you know MT of V. It doesn't tell you what is MT of V. All it tells you is that if you know what is MT of V, then you know what is m max, or vice versa. So this is 20%. So essentially, independent of the equation of state, if you know what is the maximum mass for non-rotating configuration, you know what is the maximum mass with rotating configuration. It is as if you allow for rotation, you have 20% extra mass you can put on before collapsing. Okay. One more step in this logic. There are solutions also in this region over here. These are non-uniformly rotating or differentially rotating stars. And this is the Salmon region over here. And just to be a bit more pedantic, you call supramassive star any star which is above this guy, and you call hypermassive star anything which is above m max. Okay? So in the Salmon region, there are all the models which are differentially rotating. Okay? So I had to go through all of this because of what I want to say next. And it is, what we know is that this guy has produced an object, an hypermassive neutron star, which is in the space of solution somewhere around here. We also know that this guy has produced a gamma ray burst, which in my logic means it must have produced a black hole. If it has produced a black hole, this means that this guy must have crossed this line, because this is the line after which you produce a black hole. And so essentially you have two options. One is that you go along this route, and the other one is that you go along this route. Let me tell you why route number 2 is excluded. Route number 2 is excluded because this is run very quickly in time. Essentially, this is for a system that would have collapsed almost immediately as a differentially rotating object. But we see that the gamma ray burst comes 2 seconds, 1.7 seconds later, and we see that there is a lot of matter which has been ejected. And so this means that the system has survived at least 2 seconds. And this means that it cannot be this trajectory number 2, but actually has to be trajectory number 1. And this also means that essentially trajectory number 1 must have ended up very close to the maximum mass. Okay? Because as soon as you enter the green region, your dynamics becomes very, very slow. So putting these things together, so putting the fact that we know what is the maximum, what is the mass of the system, we know how much mass has been lost because of the kilonova, which is about 14% of a solar mass. We now have an upper limit to the maximum mass of neutron stars. So we have a lower limit coming from pulsar timing, which is 2 solar masses, and now we have this upper limit in the maximum mass. Okay? So interestingly, around about 3 weeks, 4 different groups have suggested very similar results and ended up with the same conclusions, while coming from very different lines of logic. I've told you what my line of logic is. I essentially simply use this universal relation. So now we have with this object this new constraint. We can also talk about limits on radii and deformabilities, these love numbers. So what we said is just an upper limit on the mass. We still don't know what is the typical size of neutron stars. And essentially this is a question which is deeply related with the equation of state. Okay? Yet we can set some constraints. Part of the problem in equations of state is that there are as many as nuclear theorists, so a very large number. And we don't really know what are the constraints we can apply. I mean, the ones we can apply for sure is that whatever equation of state has to give you a mass larger than 2. Now we have this upper limit, but what if you just say, okay, I don't care about nuclear physics, I just invent equations of state? Well, you have that freedom up to a point, because we know that this part of nuclear physics we understand, so the very low density or small core chemical potential, and we think we also understand this part of physics, because here QCD must be valid and perturbative QCD must be valid. So you can think that, okay, I can play around with the equations of state and build any equation of state that smoothly or non-smoothly matches these guys and these guys. And that's what we've done. So we're not having any equation of state, we built 1,000,000. And for each equation of state, we built 1,000 stellar models. So we have 1 billion stellar models. So now this is statistical physics. And you can think of, okay, now you have all the possible, well, not all the possible, but a large range of equations of state. Let's use all the constraints that come from GW170817 on the maximum mass and on the tidal deformability. I've explained you the maximum mass. The tidal deformability comes from the fact that when matching with matched filtering the observed signal with the templates, LIGO has excluded some of the tidal deformability. In particular, it has said the tidal deformability has to be less than 800. Okay, so this is 90% confidence level per line for the tidal deformability. So the idea is to go from this to something else. Okay, from this, these are all the possible equations of state where you have a typical plot mass versus radius. So let me show you what happens if you have 1,000,000 equations of state. These are now probability distribution functions. Again, this is radius in kilometers versus mass. I apologize for the quality. And as you can see, this is a pretty broad range of about 2 kilometers. And here, the only constraints I'm imposing are the ones coming from LIGO and from pulsar timing. And you can see it's rather broad. You can start playing around and impose different constraints. Say you now impose also the maximum mass. Now you impose also the maximum mass and a lower limit for the tidal deformability, which comes from numerical simulations. Or you can put everything together. And then you go from this, which is a broad distribution, to something which is like this, which is a much tighter distribution. And you can take now a cut at 1.4 and look at what is the distribution function at 1.4. So this is the distribution function at 1.4. I don't want to go through all the details of these curves because there are many. Let me just concentrate on the blue ones. What you can tell is that there is now a range of about 1.5 kilometers, and you have that the maximum or the most likely radius is going to be around about 12.4 kilometers. And you can also learn another interesting thing, that is that you play around with the constraints and you don't really get a whole lot of variance. Okay, so the prediction is pretty robust. However, if you had the possibility of setting tighter constraints on the lower limit of the tidal deformability, in other words, if you are able to exclude some of the softest equations of state, then you would end up from the blue to this very peaked, nicely and narrow peaked distribution. Okay, so this is where future detection might give us a very useful input. If we can change this number over here, then we will have a much better way of telling what is the radius. Okay, let me come to the conclusions. So that maybe there's time for some questions. I've shown you that the spectra of post-merger binary neutron star signals has peaks, and some of these are quasi-universal. I've also told you that if you put this together with tens of observations, maybe in the next 5 to 10 years, we will know the radius with about kilometer precision, so 10%. I've shown you the magnetic fields I haven't shown you, but trust me, they are unlikely to be detected during the spiral, but they are important after the merger because they can lead to instabilities and electromagnetic counterparts. I've also told you that there is a tiny amount that is lost, and this is essential to explain both high A nucleosynthesis and the macronova emission. I haven't mentioned this, but this very matter that undergoes nucleosynthesis also produces light, the kilonova emission. And then I've told you how this event, as provided, already limits on the maximum mass, which is this guy over here, 2.16, and already a better estimate on what is a typical radius for a 1.4 solar mass kilometer. Sorry, 1.4 solar mass neutron star. The last is, the title of my talk is that I think that Einstein's richest laboratory is represented by neutron stars. Of course, he didn't know anything about neutron stars when he was working on gravity, but it's amazing how a single object can have so much in terms of gravitational physics, nuclear astrophysics, and of course, astrophysics. And I'm looking forward to more detections to come. Thank you.
I have a question about this event GW170817, because we observe gravitational radiation, we observe also electromagnetic radiation with high spectrum, but we didn't observe neutrino radiation. For example, Ice Cube didn't observe any trace of such radiation. What does it mean? If maybe in this event we didn't have any neutrino radiation, or maybe it was directed in a completely different direction than, for example, S2L.
So, first of all, I should mention that it's not a surprise, okay? We've seen a gamma ray burst, we haven't seen neutrinos. We've seen tens of gamma ray bursts before, we never seen neutrinos. In other words, it's very difficult to associate neutrinos to gamma ray bursts. The reason being that, the gamma ray bursts are very, very narrowed, beamed, and so we are lucky to see them, but on the other hand, neutrinos might be distributed, so our chances of seeing them is not very high. So it doesn't come as a surprise that we haven't seen neutrinos. Whether we will ever see neutrinos is a difficult question to answer. It's not clear to me that we will ever see neutrinos. Of course, as detectors become more sensitive, chances are that we will see them, but it's not clear whether we will ever see them. What we will see is the indirect evidence of neutrinos, because for instance, for powering a jet, most likely you need neutrinos. For producing the right nucleosynthesis, you need neutrinos. So rather than detecting neutrinos directly, you will have an evidence that neutrinos were involved in the game. Yeah.
Thank you for the talk, and I believe that more information one can find in your beautiful review paper with Biotti. I read this with pleasure recently. I have a question and a comment. The question is actually, can we say something now more precisely about the equation of state of this GW1708 neutron stars? Because we can limit now the total mechanical work of mass, so this does depend on the equation of state. Can we exclude at least some of these extremely strange equations or not?
Yeah, well, so, don't believe me, believe the other three that got the same answer. If your equation of state gives you a mass which is much larger than this one, then probably it's not a good equation of state. You need an upper limit, because if your upper limit is much larger than that, then that object would not have collapsed to a black hole. So the evidence that we see a gamma ray burst and therefore a black hole is telling you that the maximum mass cannot be very large. And of course, this is not a matter of believing. We know that they exist. So as a matter of fact, that detection has already ruled out a number of equations of state, and of course, there are many more that survive. Just to give you an example, I've produced 1 million of them, okay, that satisfy all of these constraints. So it's not impossible. But let's say some of the classical ones have been excluded.
And if I may, a comment also that to the kilonova emission, not only I think the secular evolution of the binary and the dynamical ejecta may contribute, but also this tiny accretion disk itself. Yes, when the black hole has formed already, we have accretion disk, and there may be some wind ejected from the surface layers of this disk, and some lighter elements, maybe not lanthanides, but some in between the mass range can be synthesized.
Yes, you are absolutely right, and I haven't remarked this enough. The secular ejection, the one I was mentioning, can go up to 100 seconds. This is not just by the upper massive neutron star. It might be produced by the system where you have a black hole and a torus. The torus will take some time to be accreted, maybe of the order, and that is going to be that will blow a good portion of its mass, maybe half of its mass, in wind, and this is important both in the nucleosynthesis and the kilonova emission. Yeah, so getting that part of the picture right is very, very important, and this is why people are now trying to do long-term, more than a few hundreds of milliseconds, radiative transfer calculations with the neutrino transfer and so on. That's a very difficult task, of course. Yeah.
Next questions?
Maybe I have one more. This is a quite famous story about so-called fast radio bars. I think started from 2006 or maybe later. What about this events in the case of this merging of neutron stars?
Okay, so fast radio bursts, for those of you who are not familiar with this, is probably the most exciting astronomical discovery of the decade. What is it? These are flashes in radio which happen on a time scale of a millisecond. So it's like a crack in your radio when you are in a car. You hear a crack, and that's actually a signal. People at first dismissed it as being, just noise, but people have realized that these are actually signals. Nowadays, I think we know about 20 or so fast radio bursts. The problem with these guys is that apart from one, they're all single events. You see them once, you search for them again, and you don't see any other emission. You search them in any other band, and you don't see anything else. So it's really a flash in the radio in the dark, and that's it. And there have been some suggestions that fast radio bursts are associated with binary neutron star merger. I think that's not a correct statement. It just doesn't match a number of things that we know. The first one is that the statistics. Fast radio bursts are extremely common. Essentially, we see once a day a fast radio. Well, we don't see them. They reach us, but we don't see them. So the population of fast radio bursts is huge, while gamma ray bursts is much smaller. So the statistics don't match. The second one is that these guys, as I've shown you, produce a big mess. When you have two stars that merge, you have a huge cloud of matter which is produced. And in order to produce a radio emission, you need a very clean environment. So I find it very hard to believe that whatever produces a gamma ray fast radio burst can be associated with binary neutron stars. Binary neutron stars just make a lot of pollution, and what is more likely is that maybe fast radio bursts are produced by some magnetar activity, something on a magnetar that is readjusting itself and is producing this radio emission, although it's not clear why it would produce it just in the radio. And then there is another model which I personally like very much, and is called the Blitzer model. And in the Blitzer model, it's very simple. You take a star, which is a magnetized star, say a pulsar, which is slowing down, and then one point will have to collapse to produce a black hole. When it does so, it's essentially in vacuum, but has a magnetic field. The magnetic field cannot, the magnetic field lines will have to be snapped, because you cannot source a magnetic field in a black hole. So you have essentially an electromagnetic wave produced by the collapse of this neutron star. And if you look at the energetics, the time scale, everything seems to match.
So thank you very much.
Yeah.
Comments, remarks? If not, we adjourn.